Good afternoon, everyone. Today I'm going to be talking about one of my PhD projects about the ecomorphological diversification of marine reptiles. Before we get going, I'd like to thank a large number of people who helped me throughout this project. When you're going around many museums and trying to incorporate lots of specimens, you need a lot of help along the way, and also a lot of help with the methods. So thank you to everyone. So I'm sure you're all familiar in some way with marine reptiles. I suppose the easiest way to categorise them is as a broad and diverse ecological assemblage. They're made up of, what is an important thing to remember is that they're not a monophyletic group. They're made up of different invasions of the ocean from many parts of the neo-diapsid tree. But they all converge on the same type of ecologies, feeding on the same prey and living in the same environments. And they existed throughout the oceans through the entire Mesozoic. And I'm sure you're familiar with all these different groups. You have ichthyosaurs, sauropterygians, different crocodilomorph groups, squamates such as mosasaurs. Marine reptiles are particularly interesting in terms of the range of morphologies that they evolved. You can see just within this small collection of marine reptiles, you have a diverse range of feeding ecologies, or diverse range of jaw and tooth anatomies, and also a diverse range of postcranial anatomies as well. One thing that interests me a lot about marine reptiles is the fact that their first invasion and the first wave of marine invasion took place in the Triassic, in devastated oceans. So you think, in the aftermath of the Permo-Triassic mass extinction event, you have this clearing out of the oceans, and then within the following 5 or 10 million years, you have this initial wave of evolution. And these marine reptiles were largely creating and evolving within new trophic niches. This kind of large-bodied marine tetrapod, it wasn't really seen before the PT boundary, but they seemed to jump in it and then explode. And another thing that interests me is how you measure this type of diversification. Do you measure it in terms of species numbers? Do you measure it in terms of the trophic structure, the number of different types of ecologies that you have? Or is there a way that you can quantify it through disparity trends? Just to look at diversity, just to give you a background on it, if you have a look, the x-axis represents geological time going from your left to your right, going through the Triassic to the end Cretaceous. And you can see in the upper graph, you have this early burst of diversity made up by these basal ichthyosaurs, basal sauropterygians and thalatosaurs. And that type of diversity is not achieved again throughout the entire Mesozoic. Perhaps just as interesting as that diversity is the range of morphological adaptations you see. So everything on this slide occurs within about 10 million years after the Permo-Triassic mass extinction event. And you have all these different morphologies ranging from filter feeding apparatus, suction feeding in basal ichthyosauromorphs, piscivorous dentition in nothosaurs, and you even have large macropredators up to around 8 meters long, and as well a host of durophages seen in sauropterygians and ichthyosaurs. And quite a few people have highlighted the fact that this kind of ecological diversity is important and it needs to be looked at further. So that's where I've tried to come in, and I've tried to find a way of quantifying that type of variation you see in those feeding apparatus. And I want to test whether the Triassic was truly exceptional. Was it a time of elevated disparity, a time when you do see a greater range of morphologies and functional morphologies? Another interesting thing about marine reptiles is the fact that they all respond to an ecological opportunity, and you have these different invasions. So when you have these different invasions and they all are evolving in response to the same opportunity, would you expect to see the same trends in each group? Would they all show an early peak of diversity and then peter out? Or would the trends be different among these different groups? And that's another thing I investigated in this project. So broadly, the aims were to focus on trying to quantify the range of morphology seen in marine reptiles, focusing on the morphology in their jaws and dentition, giving it this emphasis on feeding. Perhaps later work will include the postcranium as well. And broadly to look at disparity through time and then compare diversity and disparity trends across the different marine reptile groups. So as I said, I decided to focus on jaws, and I included 206 different marine reptile taxa, incorporating all major clades, sauropterygians, ichthyosaurs, thalatosaucians, mosasaurs, turtles, as well as a range of other smaller groups. And I measured 9 continuous traits on their jaws and scored 9 discrete characters. There's no need to read all of this, but that's just a brief overview of the type of characters that I measured. They range from things like mechanical advantage, to depth ratios, the relative area of the jaw that was occupied by teeth, And then I scored a number of primarily dental characters because they're particularly hard to quantify using continuous measurements. Once I had that data set, I transformed it into a pairwise distances matrix, which basically tells you the differences between all the different marine reptile species. And then I used that to construct some morphospaces. I then went from morphospaces to calculating temporal disparity trends. So you basically summarize the disparity found in different time intervals based on those morphospace coordinates. And these are the 16 Mesozoic time intervals that I used, spanning the entire Mesozoic. I was also interested in size, because these types of analyses often miss out size because it can get buried within the analyses. So I decided to quantify size separately by simply measuring maximum skull length in all these different marine reptile groups. And for that I had about 356 species, in which I simply measured the maximum size of the skull. So very quickly, this isn't the emphasis of my talk, but I wanted to show this. This is just an overview of all the marine reptiles pulled within the same functional morphospace. And this is PC1 and PC2, the major components. What you can see is the broad distribution of the different clades. I've highlighted them here with colour. You can see there's a lot of overlap in the centre of morphospace, but statistically all the different marine reptile groups actually have different morphospace occupation, which is quite interesting in itself. And you can see the variable amount of space that each group occupies. I don't want to dwell on this though, so I'll move on. In terms of temporal disparity trends, here you have obviously geological time along the x-axis and disparity on the y-axis. And what you actually see is this early peak of disparity, of functional disparity in the middle to early late Triassic, followed by a decline into the Jurassic, and then it steadily rises again as you go towards the latest Cretaceous. Which again, it shows that marine reptiles were more functionally disparate in their jaws and dentition in that first interval, during that first wave of evolution, than they ever were later. As John just mentioned, Lagerstatum can have a big effect on disparity, but nobody's quite sure yet how to account for it. It's both philosophically and methodologically hard to kind of quantify what the impact they have. But just as a quick visualization, I've labelled on some of the main marine reptile Lagerstatum, and you can see that just because you have a Lagerstatum doesn't mean you have particularly high disparity, or vice versa. You have things like Holzmaden, and the time interval, which is sampled where the Holzmaden fauna are within it, actually has low disparity, whereas some of the Triassic Lagerstatum are associated with higher disparity. There's also many ways to quantify disparity trends, so I attempted a number of different methods just to make sure that I wasn't getting a false signal. So, for example, rather than creating any morphospaces, I tried calculating disparity straight from the dissimilarity between the taxa. That's the top graph of this sequence. And then in the other graphs below, they're basically calculated where I only use the continuous measurements. So I deleted all the binary characters to do with teeth and just left it to the continuous measurements of the jaw shape. And as you can see, you tend to have that Triassic peak, a drop into the Jurassic, and then some degree of rise into the Cretaceous and the latest Cretaceous. An interesting thing that you can do is look at the clade contributions to this disparity curve, because remember that temporal disparity curve is of all marine reptiles pooled, and that's made up of many different marine reptile groups. And here you can see the Sauropterygians are the largest contributors to disparity throughout much of the Triassic and into the Jurassic. Ichthyosaur contribution fluctuates quite a lot depending on what representatives you have. They're the major contributors in the earliest sampled bin, which is the Olonecian of the early Triassic, but then their disparity fluctuates. And interestingly, if you look at this late Cretaceous interval, when you have this resurgence of disparity, it's actually mosasauroids and the turtles which are contributing much of that variation, and then the few Sauropterygians which remain. Just to have a look at the morphospaces through time, again, this is based on just PC1 and PC2 of morphospace. I've labelled 1, 2 and 3 on the figure so you can see where they occur. I think one is, so you've got the Anisian, middle Triassic, then you've got the Carnian, the early late Triassic, and then the Nourian, where there's a significant reduction in diversity. But you also have this, although you have reduced diversity in the Nourian, the range of morphotypes seen is still quite large. If you compare this Triassic morphospace occupation to the Jurassic, you can see that it's far more condensed within the Jurassic. Here I've sampled an interval from the early, middle and late Jurassic, and you can see all forms are clustered closer together, which goes towards explaining their reduced disparity. Finally, as you jump into the Cretaceous, I've sampled 3 intervals from the Cretaceous again, just for visualization. We've got one in the early and then a couple in the late Cretaceous. And you can see when you have the diversification of mosasauroids and turtles in the, from the Cenomanian through to the Maastrichtian, you can see that they expand the area of functional morphospace occupied, again, which might explain why you have that increased disparity in the later interval. Now quickly onto patterns of skull size disparity. This graph here, the top plot represents, so each point represents a species, a marine reptile species, and its size is plotted along the y-axis, and then it's plotted at its geological midpoint, so the midpoint of its stratigraphic range. So just to ground you in the visualization, if you look in the Triassic, you can see within that interval around here, you see you have this huge burst of variation, lots of medium-sized forms, but then you also have some very, very large forms and some exceptionally small forms. This gets kind of canalized into the Jurassic, where you have this more narrow range of sizes seen, which again, you're losing this kind of morphological variation through that late Triassic interval. And then once you go into the Cretaceous, you seem to have this expansion again, and that's added by some very small marine squamates and also the marine turtles, some of which were very small. And finally, on the results side of things, we can look at comparative trends. So just to ground you, on each of these plots, the y-axis is time. Note that the geological duration is different for the different clades. So for example, the Sauropterygians have a far longer geological duration than the Mosasauroids, for example. And in there you have a phylogenetic diversity estimate, so basically a diversity curve that incorporates ghost lineages. The second column is disparity, again calculated separately for each group. And then the third and final column is the skull size plot, again, using the same method. And you can see within the Sauropterygians and the ichthyosauromorphs, they have this early burst of diversity and this early burst of disparity. And then particularly in the Sauropterygians and the ichthyosauromorphs, it seems to get canalized. It's greatly reduced in the latter half of their history. In the Mosasauroids and Phalatosaucians, that trend isn't so obvious. So they start off at relatively moderate diversity, and and greater diversity is seen later in their history. And the same is true for disparity. They increase in disparity later in their interval. So there's this kind of dichotomy between those two groups, and that's quite difficult to explain. It's puzzled me quite a lot. There are a number of biological things it could be, and there's also a number of methodological things it could be. It could be that the Sauropterygians and the ichthyosauromorphs were diversifying during the Triassic biotic recovery, which was a great catalyst for this great morphological variation. Whereas the Mosasauroids and Phalatosaucians diversified free from any major events, and there was also far more other marine tetrapods in the environments which they diversified in. It could also be something to do with their evolutionary durations. So the Sauropterygians and the ichthyosauromorphs have very long geological durations, whereas if you take Mosasauroids, for example, most people agree that Mosasauroids were still diversifying when they were wiped out at the KPG boundary. So who knows what would have happened if mosasaurs transcended that boundary and continued with very low disparity for the rest of their history. You'd get a very different pattern if you were looking at a much larger geological timescale. So just to sum up some major conclusions, the Triassic appears to be an interval of great functional disparity in marine reptiles, and it's likely that this was due to the great variety of ecological niches available at the time. There was a large reduction in disparity through the Triassic-Jurassic interval, but that's a very staggered and long geological time frame. And the late Cretaceous represents a second exceptional interval, and that was likely due to the fact that Mosasauroids and the turtles diversified. And finally, on those comparative trends, it appears that just invading the ocean by itself may not be enough to catalyse these adaptive radiation type trends. And now I'll leave it there. Thank you.